Okay, so let me tell you what I did. I corrected the report for lab 3. For lab 3 and uploaded the correction group folder. I had a problem correcting the reports for lab 4. And I hope to resolve this issue. I hope to resolve this issue in the next few days. In the next few days. The next few days. Let's see. I still need to adjust. I still need to adjust the grade for exam 2. Okay. I still haven't adjusted the grades of exam 2 Canvas. So bear with me. Wait till, hang in there, and then I will do that soon. Let's see. This one doesn't apply. We finished chapter 8, right, on rotational kinematics. And it started chapter 9 on rotational dynamics. We will continue covering chapter 9, which we started last time. This is the one right here. Okay, and I'm just going to copy and paste what we did last time. So I can just review. Morning, I had a problem. Oh yeah, I had a problem with my software, with my correction software. I have a correction software that for some reason, it started to misbehave, and I couldn't fix it. But I will be able also. Sorry. Okay, so here you go. I'm just going to summarize what we did last time, right? So chapter 9, I will boldface that, rotational dynamics. Okay, this is more challenging than the previous chapter because we introduced concepts that are more involved. You already know that for every linear kinematic, and let's put it this way, kinematic quantity, that is an angular counterpart. But then we also have an angular counterpart for the other dynamic concepts in physics. So for a linear force, there is an angular force. For a linear momentum, there is a angular force. Which receives the name of, which is called torque. For an angular linear momentum, there is also something else that we call angular momentum. And what I want to do, I want to place this one right in here. For a linear mass, there is what I like to call an angular mass. This angular mass, there's a name, we give it the name of momentum of inertia. And there's no need for a question mark here anymore. For linear momentum, let's see. Yeah, let's put it here. For Newton's first and second law. For Newton's first and second law, there is also its angular component. Okay, well, it's yeah, let's put it this way. Here we go, right in here. There is its angular component that involves the torque and the momentum of inertia. We're going to cover that. For the linear momentum, there is also what we call angular momentum. Angular linear momentum, let's call P. There is also an angular momentum. No need for the question mark anymore. For the linear kinetic energy, comma, that is a rotational kinetic energy. For the linear work that we defined previously, that is also a, let's call it an angular work, right? Angular work, and I'm going to cover all of that. For the work kinetic energy theorem, we also have its angular counterpart. So it's just a matter of repeating what we did before, but using different ideas, different concepts.
Professor, other student wants to join the call. Oh, never mind.
Yeah, sorry, I didn't notice that. Thank you for letting me know. Sorry, folks, I didn't see you waiting there, so I just saw it now and I let you in. There are 3 students there hanging there. And the, how do you say, in the waiting room, okay? So that's what we're going to be doing this, and we started doing that. We already started defining these quantities, right? The angular counterpart for the force is the torque. It's called torque. And that's the equation for the torque. Based on those definitions, on those illustrations that we saw before. Here you go. Put it here. Let's go down here and no, let's see. Nope, gotta go further down. That's linear momentum. That's collisions, right? Collisions. And that's the angular quantity. That's chapter 8. And let's take a look. Okay, right in here. Just reviewing what we saw before. Suppose that we have a rigid body. Don't forget, we are dealing with rigid bodies, not with extended object, right? And this rigid body has a axis of rotation that with respect this vertical axis along the y direction. Okay, here you go. And this rigid body, an example of a rigid body would be the door that we have that has a hinge. The door can rotate around this hinge that coincides, the axis of the hinge coincides with the y-axis. If you look from the top, that's going to be how we're going to see, right? The door and the hinges are here. Here's the axis of rotation of the hinge. If we apply a force right here at this spot on this door, we have to define also the point of the vector position of the point of application of the force, which is going to be this one here. I'm going to put this force F in the previous drawing right here. Okay, this is the vector position R. And when we do something like that, we do generate a torque. We do generate a torque. The door is going to, will tend to rotate along this direction because of the torque. This is going to be a counterclockwise torque. Counterclockwise torque that I'm going to oops, no, this is not what I want. I want this one here. Counterclockwise torques are positive torque. And clockwise torques are considered negative torque. Format shape, we need the yeah, right in here. This one will be my R. This is going to be, and again, I'm going to just use different colors so you can identify the colors. Here you go. That's the torque. I will make this guy red as well in boldface. Okay. Going back here. Okay, theta, theta is going to be the angle between R and F. Okay, in the above formula, R is the vector. No, let's start with F. F is the force, the vector force, by the way, the vector force applied to the rigid body. R is the vector position of the point of application of the force, and theta is the angle that the vectors R and F make with each other whenever they are placed tail to tail. That's how we measure the angle theta. Notice that the larger the force, the higher the torque. Also, the larger the R, the higher the torque. And finally, the closer the angle is between R and the closer the angle between the two vectors is to 90 degrees, the higher the torque as well. If we are going to exemplify this type of torque, right? The highest torque is going to be this one here. Among all those illustrations here, the highest torque of all is going to be this one here, because the vector position of the point of application of the force is the largest possible. Not only the largest possible, but it also makes an angle of 90 degrees with the force vector. This is the largest of all. This one here is the second largest. And the other two may be the third or the fourth largest. Okay, which one is going to be the third largest? Which one is going to be the fourth largest? Is going to depend on this angle that you see here. We cannot say for sure that this one is larger than this one, or that this one is larger than this one. We cannot say for sure. We need to know the angle. So the angle and the distance R, so you can come up with a proper decision, judgment. But definitely this one is larger than this one, and this one is larger than this one. But this one is also larger than this one. because all those force vectors are the same, the magnitude of the force vector. Okay, so that's what we did. And what else? Here you go. If you so what do you have? What we end up having here? We end up having here that the actual force that's producing the torque is not F, but it's just its component perpendicular to the position vector. Okay, can you picture that? So if you go ahead and project this force here along an axis that's perpendicular to the position vector, you're going to see that it is exactly this component of the force that's producing a torque for this specific example. Okay, so let me note, I'm going to erase everything else here. And we are just going to concentrate on this one. Consider this a specific example. Okay, I'm going to make my force a little even longer than that, higher than that. Okay. Notice that this angle theta that you see here is exactly the same angle as this one here, right? Exactly the same angle as this one. When you put the R and vector V and vector F tail to tail. Okay, so let's take a look at this component. So now we're going to have one vector force here. You go on one component, right? I'll put the F right in here. And I'm going to dash it as well so you can understand that this is a component. Just to illustrate that this is a component. And then we're going to have another component that's parallel to the vector position. Like that. Yeah, this one is better. Okay. So this one here is going to be the component perpendicular to R, component of the force perpendicular to R. And this is going to be, the other one is going to be the component of the force parallel to R. That's the symbol for parallel. And this is a very useful definition, okay? The concept of torque is a very useful definition. Let's go back to this one here. From the above formula, note that only the force component, only the component of the force perpendicular to the vector position of the point of application of the force, with big, right? R, is responsible for the torque. The other component parallel to R that has no torque whatsoever, produces no torque whatsoever. Okay? Note see that. The unit of torque is, note also, note see that the unit of torque is, what's the unit of torque? The unit of torque is going to be the unit of the force plus the unit of distance. It's going to be Newton meter. Do not confuse. If we go back and recall the unit of joules, right? Joules, J, is also Newton meter, which is the unit of work as well. So the unit of work is the same as the unit of torque. Okay, so watch out for that. The only difference is that work is a scalar quantity, whereas torque is a vectorial quantity. Okay, they may have same units. They may have same units, but their definition, right? Their definition is distinct. Okay, what's the definition of torque and what is the definition of work? Okay, remember, we go, that's the definition of torque. The definition of work is what? The definition of work is going to be F, yes, it's going to be F. It's going to be delta X, but instead of sine of theta, it's going to be what? Cosine of theta. So coincidentally, so it is a coincidence. So it is a coincidence that their units is the same. Okay, it's just a coincidence. There are two different concepts that are also very useful. These are different concepts. These are different concepts that are very useful. One is a scalar, the other is a vector. These are different concepts that are very useful, but has the same unit. They're not the same, they're different, and it's just coincidence that their unit is the same. So what else we wanna do? We want to you already know that that Newton's first law applies whenever the net force is equal to zero, right? Equal to zero. Right? So if you recall, in other words, if net force is equal to zero, what does it imply? It implies that an object will be either at rest or moving with constant velocity. By the way, the same applies to the net torque. Okay, and that would be that would be Newton's first law for its angular counterpart. That's the angular counterpart for the Newton's first law, whenever net torque is equal to 0. Okay, so here you go. If you have net torque equal to 0, comma, we have a similar situation. Similar situation. In other words, the rigid body will not be rotating. In other words, omega must be equal to 0, or omega is going to be a constant. That's Newton's first law for a rigid body. Oops. Font symbol. Yeah. Let me copy this guy here. Like here, better. Okay. And now I'm gonna come back to the table that we started working before. He go, my light went out again. Hopefully you will be able to stay here long enough before my UPS runs out of juice. Okay, so this is the table that I came up with. Linear and angular quantities, right? Position, displacement, average velocity, instantaneous velocity, average acceleration, and instantaneous acceleration. Now we can add 2 more parameters, right? We can add the force, the linear force, and the angular force. Okay. In this case, the angular force has a unit of Newton meters, whereas the linear force has a unit of newtons only. And equilibrium condition, that's what we call equilibrium condition, when we have net force equal to 0 and net torque equal to 0. Someone is trying to get in. Okay, so light came back. Hopefully it stays like that. I cannot get my C. There's a student. Oh, here you go. I got it. No, that is try to get in. Okay. And that will be the equilibrium condition. Oh, by the way, equilibrium condition for a rigid body is not just net torque equal to 0, but the net force also has to be equal to 0, okay? Not just one. So we have a more strict situation for a rigid body to be in equilibrium, okay? The following 2 conditions must be satisfied simultaneously. It's not just the net torque has to be equal to 0. You also have to have net force equal to 0. And by the way, you can have a net torque equal to 0, but a net force not equal to 0. Okay? It's possible. It's possible. Note, see that it is possible for a rigid body to be subject to a net torque of 0, but a net force non-zero. It's possible. Let me give you an example. In this specific case, in which the net torque is equal to 0, but the net force is non-zero, the rigid body is not going to rotate, okay? But it's going to be accelerated linearly. In this specific case, the rigid body is not going to rotate, or, in other words, or will rotate with constant angular velocity, comma, but the whole rigid, the whole body will, can be, may be accelerated, okay? I'm gonna give you an example. That's why we have to come up with the second, with this second condition. So here we go. Let's see. I can. Here goes. Here's the case of a single force applied to my rigid body, right? It has. In this case, we have a negative torque because the torque is clockwise. Torque clockwise means that the vector torque is pointing into the board. Okay, and we can come up with some examples here. And now here we go. We have this displacement. Let me see here. Oh, okay. Translational equilibrium and with no rotational equilibrium. Okay. A rigid body may be in translational equilibrium, but not necessarily in rotational equilibrium, and vice versa too. It's a very interesting situation. It's not obvious, but it's a very interesting situation. So here you go. Here I'm depicting my rigid body like this rectangle, okay? The center of the rigid body is what we call the center of mass. It is center of mass. And I'm going to apply two forces. One at this edge and the other one at this other edge, okay? Because the vector position of those two forces are exactly the same, the magnitude, not the vector position, but the magnitude of the vector position of the two forces is exactly the same. And I'm gonna even, put here F1, want to distinguish that from you, for you, so it's clear. Subscript. And the other one is gonna be F2. Strictly speaking, I'm supposed to, here is going to be R2, okay? And here is going to be R1. I'm gonna put them in red color, so they are associated with that specific vector. With one important case, you know what, let me put a vector there, right? First case, okay? One, rigid body in translational equilibrium. Translational equilibrium means net force is equal to 0. I'm gonna put the vector here too. Let's do it in the right way, right? Here you go. Use the right notation. Here you go. Net force equal to 0, but not in rotational equilibrium. And rotational equilibrium means what? Net torque different of 0. And I'm gonna put a vector here as well. Here you go. Not equal, but different of 0. And I'm going to copy, not, I'm going to do more than that. I'm going to go ahead and copy and paste right in here. So I have the proper vector notation. Let's see here. Okay, my goodness, ended up to be very poor. What a lousy vector. Okay, better now. Yeah. Ooh. No, I don't like it. That's better. Yeah, here you go. Net. Yeah, now we have it. No, it's not net, it's one. Yay. Hey. It's supposed to be one here. Good. And now I see it's too large. I'll make it smaller. 32, 30, 40. Okay. And the other one here is going to be F2. What else? Since it's in translational equilibrium, and I'm going to do the same for R1 and R2. I'm doing that, all of that, just to get the, I'm doing all of that just to get the right vectorial notation there. Okay, I don't need that anymore. R1. This one is so big. But that's okay. In this specific case, okay, I'll have to fix the other one. I'll do that some other time. Next semester I do that. Don't forget this. All those are all vector forces, right? Here you go. Translational equilibrium means what? Translational equilibrium. In order for this object to be under translational equilibrium, yeah. I'm not gonna do here from scratch. Equation. Here you go. Now it's better. Good. Okay, that's better now. Translational equilibrium means that with a minus sign here. Okay. Make a little bit larger. One a bit. Yeah, and now I can copy and paste it here. And copy and paste here. But there is more. It's not just that. In this specific case, you know, R1 is equal to minus R2 as well. In this specific case, it doesn't have to be R1 equal to minus R2. The magnitude of each torque is going to be the same. But if you notice, well, okay, this force here will generate a counterclockwise torque. Do you see that? And this other force here, it will also generate a counterclockwise torque. There is translational equilibrium, but not rotational equilibrium. Okay, so here we go. In this case, torque of one is going to be, even though the force has negative value here, right? There's a negative sign. The torque of one is going to be equal to the torque of two in this specific case. I'm even going to illustrate this torque like that. With a arrow in the counterclockwise direction. Okay. This one here I will call tough, right? Tough. Not tau, but tough. Tau one. That's going to be green. That's going to be, no, not this one. This one here I want. This one here, yep. And then the other one is also going to be similar. Oh, raining very hard here. That I'm gonna put it in a different color. Which color we're gonna choose here? Let's choose this one here. This one here. Like that. This is translational equilibrium, but no rotational equilibrium. It is this rigid body is going to be translating at constant velocity. It's going to be at rest, either at constant velocity or at rest, but it will rotate and will have an angular acceleration because it has a net torque. Okay. Now what's the next? Object under rotational equilibrium, but no translational equilibrium. Here you go. We have force 1, force 2, R1 vector, R2 vector. This force is generating a clockwise torque. This other force is generating a counterclockwise torque. So the torque generated by this force is going to counter the torque generated by this other force. But there will be a net force because those two forces we're going to be adding to the right. Okay? And then the question is, how can we have an object who is under translation equilibrium and rotational equilibrium simultaneously? That's here a situation in which we have both of them. Okay? This force is imparting a counterclockwise torque to this rigid body. This other force is imparting a clockwise torque. Okay, but because they're being applied at the right positions, right? The net torque, the net force is not going to be zero. The net force is going to be zero. Net force zero, net torque zero. Okay. So that's an important situation in physics. Let's take a look at this one here. And here what we have is the case of a rigid body as well, producing multiple torques. Okay, force 1, force 2, and the weight. This force 1 is producing a counterclockwise torque, a positive torque. This force is producing a clockwise torque. And is with respect to this point of rotation here. Okay. Okay, light went out again. Let's cross the figures. And because we are taking the, and by the way, torque must be taken with respect to any point, okay, that you consider. In this specific case, the point of the torque that we are taking the torque with respect to the center of mass of this object. So those two forces are going to, F1 and F2 are going to have a torque. But the weight will not have a torque because the point of application of the force is at the point where we're choosing the rotation of the object. So let's write that down there. Okay, net force. Example 3, let's take a look here at the book. What you see in there is an example in the book, okay? Light went out again. Let's okay, here you go. Yes. I'm going to show you an example. There is the book, and so you can understand better this concept. One, two, and three. Okay, here you go. This is the example in the book, okay? That we have. You saw that illustration in my figure, right? We have this bar, okay? Shows an overhead view of a horizontal bar that's free to rotate about an axis perpendicular to the page. But this axis coincides with the center of gravity, center of mass of the object. Two forces act on the bar and they have the same magnitude. However, one force is perpendicular to the bar and the other makes an angle phi. Here you go, phi with respect to it. The angle phi can be 90 degrees, 45 degrees, or 0 degrees. Rank the values of phi according to the magnitude of the net torque. Okay. So what about the force here? Two forces act on the bar and they have the same magnitude. Same magnitude. Okay. Remember, this force has the same magnitude. Consequently, the torque of this force is lower than the torque of this one. Okay, the point of application of the force, the distance is the same, the force is the same, but the angle is different, right? Just what I mentioned before. Here is the condition of rigid objects in equilibrium. Net torque equal to 0, net force is equal to 0. Okay. And we have another example right in here. A woman whose weight is 530 newtons is poised to the right end of a diving board with a length of 3.9 meters. The board has negligible weight, and is bolted down at the left end while being supported by this fulcrum here. Okay, what the book didn't say is that this board here is a rigid body, okay? Not those regular boards that we see out there that they bends back and forth, right? This board here is a rigid one. It doesn't bend at all. Find the forces F1 and F2 that the bolt exerts on, exert on the board. Find the force F1 and F2 that the bolt and the fulcrum exerts on the board. Okay, that's a very good example. Okay, we are going to do that. We gotta do a negligible and it's both to the left. Yeah. Okay, so we go. I have to do a drawing from scratch. And we are going to have a bolt here. Okay, that's here you go. There's a downward force here. Let me get that here. It's going to be different. Here you go. Downward force here for the woman. 3.9 meters. I'm going just to show the forces. Okay, there will be a fulcrum that I have to draw here as well. The fulcrum is going to be something like that. Okay, 3.9 meters. I'm gonna put 3.9 meters here. 3.90 meters is the length of the board. Let me take this one apart here, put aside for now. This fulcrum, is preventing the board from going down. Move downwards. I'm gonna put aside here. The board has a negligible weight, so you don't need to consider the weight of the boat. I'll put this one aside here as well. So this fulcrum is applying a force as well. Okay, the board on the board. And here you go. And this boat is preventing this end of the plank to rotate, right? That's what this boat is doing. So the only possible way that this force of the boat is going to exert is going to be downwards. It's instead of W, let's call it. Let's see. I'm going to keep the same. I'm going to use this one right here. Force, you go. Force of the boat. Example 3 in the book. I'll write that down here. Example 3 in the book. Example 3 in the book. Okay. And we do have this F. We're going to have another force applied by the woman. And that I'll call the weight of the woman. Like that. And let's change colors. Okay, folks. Right now, we don't have any electricity here in my place, okay? So we're running here under the UPS. I hope the electricity returns before I run out of power, my UPS, okay? My UPS device. So if you're still there, just wait a little bit more. If I go offline, just wait a little bit there online, so you can do the lab. Here's the center of mass. I'm going to take out the center of mass because you don't need the center of mass. Those are the forces that we have. And what else do we need? If we go ahead and take, and by the way, the torque can be taken. I need to write it down in the notes too, okay? The torque of a force, of any force, can be taken with the torque of a force, right? Can be taken with respect any point in the rigid body, okay? In the rigid body, okay? Just make sure that the torque of every force applied to the rigid body, is taken, is calculated with respect this point. Okay? save. Let me save my stuff here before the light goes off, before I run out of power. Yeah, I'm still okay. Hearing the countdown here of my UPS device. I think we have 15 more minutes here. If the electricity returns, we'll be able to continue. If the electricity doesn't return, then I will ask you to hang in there for some time, okay? Let me write that down here, so in case that you didn't hear me. Okay, right now, I have no electricity in my place, but my UPS device is feeding my computer and modem. My computer and modem. It may last another 15 minutes. It is 9:48 right now. If I go offline, please stay around. Please stay logged in. So we can do the lab, okay? Here you go. Now, just like I said, your point of application of the force, of each of those forces, can be taken with respect to any point, any convenient point. Okay, you can choose this point to be this one, you can choose this point to be this one, you can choose this point to be this one, you can choose the point to be the center of mass of the object, or anywhere along this bar. Okay, and it is right now at this point that you have to come up and say, look, what's the most convenient way? What's the most convenient point to take the origin of my vector position, okay? The vector position of application of the force. And let's go back here to the, okay, here you go. Find the forces F1 and F2 that the bolt and the fulcrum respectively act on the bolt. When you have a problem like that, you know this force. Going back here, you know this force, but you do not know this force here. You do not know this force here. When you have a problem like that, very good way of solving this problem is to put your point of origin of your vector position either here or here. Okay, that's the most convenient. Why is that? Because if I think about that, if I put my point of reference right in here, the torque of this force, this unknown force, is going to be 0. Okay. Similarly, if I put my point of reference right in here, the torque of this F2 is going to be 0. And what's the advantage of having the torque of either this one 0 or either this one 0? You simplify the equations, okay? You simplify the equations. You take out one of the unknowns from the equation. That's why. And let's see what the book did. The book took the point of reference as being the bolt. That's what the book did. Okay. And let's say the distance here. Okay, the bolt has negligible weight and is bolted down at the left end while being supported 1.4 meters by a fulcrum. Okay, that's what the book did. He decided to place the axis, the imaginary axis, right in here at this spot. And you're going to see what's going to happen. Okay, I call that LW, and he called that LW and L2. Okay. So we go. Example 3. Example 3 in the book. No? 3 forces. Board in equilibrium. Remember, board is a rigid body. The book didn't say that. So the board does not flex. This board does not flex at all. Find three forces, F1, F2, F3, F1, F2, and F3 acting in the board. You know F3, you know F3, the distances of all three forces, but you do not know F1 and F2. Find F1 and F2. Board is a rigid body, so the board does not flex at all. Okay, solution? Okay, so we go ahead and start with the condition of translational equilibrium. That's the condition of translational equilibrium. Net force is going to be F1 plus F2 plus F3. F3 is what I call the weight, downwards weight. Okay, I'm going to put it W here. And we have a negative sign because the force is downwards. Okay, so we end up with it for the translational equilibrium situation, we end up with something like that. Okay, unknowns, the F1 and F2 are unknowns. That's why they are both faced. That's my first equation. We have one equation with two unknowns. We cannot solve this problem. One equation with two unknowns. Okay, we have to get a second equation. The second equation is what? Rotational equilibrium. It's the equation of rotational equilibrium. And in the case of the rotational equilibrium, it's going to be like that. Here you go. Looks like I'm running out of power right now. Now we have W times the distance from the boat. The book call it L. I'm going to put D, okay? F2, going back here, F2 produces a counterclockwise torque. Let's see, no, F2 produces no torque whatsoever. No, wait a minute. Yeah, counterclockwise torque. This one produces a clockwise torque. So should be F2 again is, yeah, is going to be a counterclockwise torque. We know this distance here, and this one doesn't produce any torque whatsoever. Doesn't produce any torque whatsoever. Okay. That should be 0. Because it's the point of application of the force. Let me both face it. Both face it, okay? So from this equation alone, we can get F2. Okay, from this equation alone, we can get F2. F2 divided D divided by D2. And now that I got F2, I can substitute in this other equation here to get F1. See that? So my power is running out. Please don't leave. Okay, stay around.